Hello and welcome to Lesson 43, Part 3, Gamma Decays. Remember there are three parts that I am breaking up this lesson into, so if you have not already looked at Part 1 and Part 2, I'd suggest you go watch those as well because they do inform what we are doing here, which is looking at only gamma decays, at least at the start, and then we're going to talk a little bit about measuring radiation, also the modern ways that we try to measure radiation. So, gamma decays themselves, they have this symbol that kind of looks like a letter Y, but it's kind of more swoopy and has a loop at the bottom. Gamma radiation is a very hazardous form of radiation because it's very difficult for us to block exposure to it. In fact, if I really want to stop it from, if I've got something in front of me emitting gamma radiation, in order to block it, I'm going to need something really thick, like several centimeters worth of lead or like half a meter or more of concrete, something like that. And that's because of the nature of what gamma radiation is. It's not deflected in a magnetic field because it has no charge. It is not ionizing radiation because it does not have a charge. It's not a particle. It is true EMR. It's the EMR that we talked about as being very close to the end of the electromagnetic spectrum when we were studying that way back in chapter 13. Gamma decays are a burst of radiation that's given off, most often after an alpha or a beta decay has happened. Because you got to imagine, after going through an alpha or a beta decay, either positive or negative, the nucleus has chucked out parts of itself. The nucleus is in a more energetic, excited state just because of chucking things out. So to reach a lower energy state, it basically just barfs out this burst of energy in the form of a gamma photon, a single burst of energy coming out that does have quite a bit of energy, so has quite a high frequency. But because it is not a particle, it does not have any A or Z values of its own. So when we look at the A and Z values of our daughter nucleus, it's still the same as what we started off with. Probably easiest to see this in an example. I'm going to go back to the beta positive decay that we showed in example number 4. And again, this would be me telling you this, that after that beta positive decay occurred, the daughter nucleus, the argon 40, is in a higher energy state. It's an excited energy state, so it gives off a burst of gamma radiation. So I'm going to use the argon 40 as my parent nucleus in a new decay that releases gamma, but gamma has no A or Z values, so my daughter is still argon 40. People usually try to read way too much into this. We're not saying that something super complicated is happening. It's just a burst of energy coming off, and the nucleus that we started with is still the exact same nucleus we've got at the end. Now, another thing that could occur, though, given something like this, is either we will tell you something about the frequency of the gamma burst that was detected, or maybe its energy measured in mega electron volts. And with either of those, you can take energy and solve it for frequency, E equals HF, or if you have the frequency, you could solve for the energy. But one way or the other, it could be something that you play with to kind of figure out the characteristics of that gamma burst that was given off. Now, honestly, that's all there really is to gamma decays themselves. But what I'm showing you here as the daughter nucleus from one decay became the parent of the next, well, that's something that we can refer to as a decay series. And a decay series is just us showing that by the time we get to the end of any particular decay we're looking at, we're probably not describing the most stable isotope in the universe. That'd be something like hydrogen 1. No, we've got something else, so it'll go through its own decays. There's two different ways that we can show a decay series. The long way, which is pretty much what I just showed you, or a shorter way that only shows daughter nuclei. So let's look at an example. I tell you that Thorium-226 will go through a decay series, several different decays, until we produce astatine-214 as the final daughter nucleus, or at least where we're ending things. So if I was going to show this the long way, I could show thorium-226 doing an alpha decay to become radium-222. The radium-222 becomes my new daughter nucleus and goes through a beta negative decay and makes actinium-222. Don't forget that antineutrino there. And then the actinium-222 goes through its own alpha decay, makes francium-218, and then the francium does its final step, an alpha decay, to make astatine-214. Now, what I'd suggest is you might want to pause the video here for a moment, because I did go through those quickly, and just kind of trace as the daughter nucleus of one decay becomes the parent of the next, and just double check that you can see that all of the rules for conservation of nucleons and charge have been followed all the way through. And remember, this is the long way. This is the full way to show it so that we see absolutely everything. But since you are familiar with alpha and beta decays like this, maybe we could write it a shorter way. Maybe I just write the daughter nuclei. So I still start with thorium-226 becoming radium-222, but then instead of showing all of the alphas and betas and even antineutrinos that are being given off, I just show progressively the next daughter nucleus, the next daughter nucleus, the next. It's a lot quicker to write it this way. And just by me looking at the numbers for the A and Z values, I can figure out whether an alpha or a beta decay has happened. And in fact, this would be a great way for me to show you something like this on a test, because I could write it out the short way, and then I could ask you to identify basically at each of those arrows, there's 1, 2, 3, 4 of them. This would be great for a numerical response. What type of decay happened to result in the next daughter nucleus? Now, measuring radiation. This is something we also need to be aware of, at least the basics of it. There's a lot of ways that physicists have tried to figure out to best measure radiation, and part of the problem that we do have is that in the very earliest days, like, think Henry Becquerel, the Curies, stuff like that, they didn't even realize the danger of the energy that was being released. We have to get up into, about the 1930s, 1940s to really figure out that, hey, there's something that might be bad here. Now, one of the older units to figure out the amount of energy that's being released as radiation is called rads. Obviously, the name makes sense, radiation, rads. But all that it does is it measures that for each kilogram of tissue of, say, for example, you've absorbed 0.01 joules of energy from the radiation. You know what? That's actually not that much radiation. And that's why this unit isn't so good for us, because during typical radioactive decays, you can get into lots of rads then. The unit is too tiny. So they switched it up to something called grays. In grays of radiation, it's still the same sort of method, but now it's 1 kilogram of your tissue absorbing a full joule. That means that really 1 gray is just equal to 100 rads. But then, as physicists were learning more and more about radiation being released, they realized that, for example, being in a room with something emitting alpha radiation and something emitting gamma radiation would be two very different situations, even if the amount of energy being released was the same, because of how much it can penetrate our bodies and the damage it can cause because of that. So that's where we get to sieverts, which is our more modern method. And it uses something called relative biological effectiveness. Now, it's not as simple as this, but it would be kind of like saying alpha, we multiply the grays by 1. Beta, we multiply the grays by 5. And gamma, we multiply the grays by 20. You see, if we're doing something like that, we're taking into account that the gamma is much more dangerous to be around than the alpha, even if the amount of radiation, the joules of energy that are coming at me per kilogram of me are effectively the same. Sieverts takes that into account for us. Now, you're not expected to do a whole bunch of like high-end calculations with this. There's no formula for it or anything like that. But you are supposed to kind of know a little bit about it. So what I suggest is just kind of keeping in mind that here in Edmonton, we receive between, as an average person, about 0.5 to 1 millisieverts in a typical year. So how does this compare to other situations? Don't worry about memorizing this. This is just for you to see. If we're going to measure things still in millisieverts, we'd have to be talking about 10,000 millisieverts, about 10 sieverts, as being for certain fatal within weeks of being exposed to it. If you start dropping down from there, 6 sieverts, 5 sieverts, 1 sievert, you can see we're dropping down there through the thousands of millisieverts. We are talking about radiation that is still significantly harmful. The Chernobyl workers did die from exposure to 6 sieverts of radiation. But if we can get lower than that, we do see that we start having the chance of being able to save the person if they receive proper medical care and, let's be honest, they have some luck. Getting down into about the hundreds of millisieverts range, this is where it is still definitely dangerous, because what we could even see is that that person's getting that kind of exposure, but maybe it's happening every day for several weeks. That would still be significantly dangerous. Dropping down into like the tens of millisieverts. This is where people that work in industries that involve radiation, they will be exposed to this. And that means that they do have to take into account their radiation exposure and maybe limit things like their own getting x-rays done or something like that, because they don't want to just pile on more and more on top of this. It might also be that, like in the example of an airline crew there, they're actually mandated to take a certain number of months off every year where they can't be flying, because up at those high altitudes they're being exposed to more radiation. Now we're talking about the annual background radiation that an average person is exposed to. And we can't get away from that. There are naturally occurring forms of radiation on our planet that have nothing to do with anything we do in our modern day world. Right under the feet, right under our feet here in Alberta, we've got the Canadian Shield under us. It's releasing a little bit of radiation. There's deposits of uranium further north of us. Anywhere on the earth, there's going to be other exposure causes. Heck, even a banana. And there's a video coming up too that I'll mention that you can watch about that. And then you get into the ones that are comparatively quite low, and that's why you can have a few dental x-rays. You can have a couple of chest x-rays. You can have exposure for medical reasons where it's still just kind of contributing on the level of your annual radiation that you get exposed to just living on the planet. So, if you're interested, I've got a link here to a video from the 1950s. It's a commercial where they used radioactive isotopes to detect dirt that your cosmetics could take away and help you clean off. It's scary. And then another video where we visit some of the most radioactive places on Earth. I do suggest you watch these YouTube videos separately and enjoy them for all the information that they have. That brings us to the very end, though, of this section. I hope that you've watched all 3 parts of this video and that you now have a better idea of alpha, beta, gamma, the history of radioactivity, ways of writing out decay series, and different methods of measuring radiation, different units. Have yourself a good day. Bye. Bye-bye.